Hi everyone, welcome back to my channel. In today's video, we will discuss about exact differential equation, and in the end of the video, we will learn how to solve it by taking an example. Okay, a differential equation, a differential equation of first order and first degree can be expressed in the form mxy dx plus nxy dy is equal to 0, where both mxy and nxy are functions of x and y. Now, if this function mxy dx plus nxy dy can be expressed as the differential of a function of uxy, that is, we can write this mxy dx plus nxy dy as differential of the function u of xy. Then we call this equation mxy dx plus nxy dy as exact differential equation. Now, take some simple example. Now, the simplest example we can take is, suppose we have dx plus dy. Now, one can easily show that this is nothing but d of x plus y. Okay, let us take another example. Suppose we have x dy plus y dx. So, this can be written as differential of xy. Because by the product rule, we have the derivative of xy is nothing but x of differential of y plus y times differential of x. So nothing but it is x dy plus y dx. Okay, so now we have a very important theorem which tells us about the exactness of an ODE. So the theorem says, so let me state the theorem. So theorem says the necessary and sufficient condition for the equation mxy dx plus nxy dy equal to 0 to be exact if del m del y is equal to del n del x. So that means the partial derivative of m with respect to y is equal to partial derivative of n with respect to x. So now go back to the second example where we take x dy plus y dx is equal to 0. So note that here this is m because it is with dx. So which one is with dx? We call it m, and the other one is n. So if we find what will be del m del y, so the partial derivative of y with respect to y. So we know it is 1. So similarly, if we try to find del n del x, it will be derivative of x with respect to x, it is also 1. So here we see that this del m del y is same as del n del x. So it is exact as we have seen before. Okay. Now let us take another example, which is 3x squared y plus xy plus e power x dx plus sin y plus x e power y dy. So here we have m of xy is 3x squared y xy plus y. Now del m del y will be 3x squared plus x plus 0. So it is nothing but 3x squared plus x. On the other hand, what is n? N is sin y plus x if y. So del n del x is nothing but, so derivative of sin y with respect to x is 0, and this derivative will be ey. So we see that, so del a is not equal to del n del x. So we can say that this is not exact. So to check the exactness, what we need to do, we just have to calculate del m del y and del n del x and see it is equal or not. Okay. So in this video, we will learn how to solve exact differential equations. So let the equation m xy dx plus n xy dy is exact. Then by the definition of exactness, there exists a function p of xy such that d of p of xy is equal to mxy dx plus nxy dy, and it is 0 given. So we have d of xy is 0. So differential of uxy is 0. So we must have p of xy is constant. So which is the required solution. So we have to find the required function uxy to solve the differential equation. Now let's see how to find uxy by taking an example. Okay. So consider an example: cos y plus y cos x dx plus sin x minus x sin y dy. So now we have to identify what is m and what is n. So the one with dx must be m, so this is m, and the one with dy is n. So here we have mx of mxy is cos y plus y cos x, and nxy is sin x minus x sin y. So we need to find del m del y. So the partial derivative with respect to y is the derivative of cos y is equal minus sin y. We know here x is constant, so cos x will be cos x, and derivative of y is 1. So it will be minus sin y plus cos x. And what will be del n del x? It is nothing but cos x minus sin y, because here y is constant. So here we get del m del y is same as del n del x. So we can conclude that the equation is exact. So we call this equation as number 1. So we say that the equation 1 is exact. Okay. So now, since the equation is exact, there must exist a function u so that this m dx plus n dy is equal to differential of uxy. Now, if we expand the right hand side expression by the chain rule, we have this will be same as del u del x dx plus del u del y dy. So by comparing, we must have del u del x equal to m. And what is m in this case? Cos y plus y cos x. And similarly, del u del y is n, which is nothing but sin x minus x sin y. So we call this as equation number 2 and this is equation number 3. Now we have by equation number 2, we have del u del x is cos y plus y cos x. So if we try to find uxy, that means then we have to integrate this function with respect to x. Now since this is a partial derivative, so this the variable y must be constant. So we will perform this integration by fixing y, by keeping y as constant, and the integration with respect to x. So cos y is constant, so integration will be x times cos y. And y is fixed, so integration of cos x is sin x, so y sin x. And since it's a integration with respect to x variable, so we must have a constant in terms of function of y. So we need to we have to add a function of y, hy. So this is our u. Now, if we find partial derivative with respect to y, then we have del u del y. By this expression, we have minus x sin y plus sin x plus h prime y. Okay. Now, if we compare this number 4 with 3, so comparing 4 and 3, so we must have h prime y is equal to 0. So we have hy is equal to some constant g. So we have u of xy. The required function is x cos y plus y sin x plus d. And since we know that u of xy is equal to constant is the solution, so the required solution is x cos y plus y sin x plus d is some decline. So we can write it as x cos y plus y sin x is a constant c, where this c is nothing but d prime minus d. So all c, d prime are constant. So these are the general solution of the given ODE.